We have Chuck Allen with us. He's the current vice president of the Astronomical League, and he was also the past president of the Astronomical League. He's was past president of the Louisville Astronomical Society, and also he's part of Evansville Astronomical Society. Some of you might remember last summer I did a presentation on the Astronomical League's programs you can complete to like earn badges and certificates, and it looks like, have you earned all of them, Chuck? Or close to all?
Oh, heavens, 37, but there are a lot more than that.
Oh, nice.
Yeah.
Nice. And he also has done over 500 presentations, so this is going to be one of those. And also, he presented with us in, was it 98? Probably, so at Fox Island. So I don't know if any of you were at that meeting or remember that, but yeah. So thank you so much for joining us, and whenever you're ready, you can take it away.
Okay, thank you. I wonder, I would like to ask if everyone would mute during this, just so there are no background noises. And if you have any questions, just unmute and feel free to ask. I'll be happy to do that at any point during the program. Yeah, it was 23 years ago when I spoke with you, and I don't know that I have another 23 in me, so hopefully I'll be back before another 23 passes. I would like to make one comment about the COVID effect on astronomy, because I've seen it firsthand through the league. Most of the telescope companies that we deal with routinely are experiencing something close to 400% demand over normal for telescopes. If you've tried to order anything, you've probably experienced this. We've been participating in live events and also global star parties with the assistance of Scott Roberts of Explore Scientific. And those have been drawing anywhere from 6,000 to 21,000 people. So a lot of people are turning to astronomy right now because of COVID, and I think that's going to be one perhaps silver lining of this rather disastrous couple of years that we are experiencing. So tonight, what I'll be talking about is something called cosmic horizons, but really we're going to be talking about three kinds of horizons. Horizons, there's nothing magic to them. It's simply a limit on how far you can see. So let me go ahead and share a screen and we'll get started here. Okay, so we're talking about how far you can see, and there are three different kinds of limitations on what we can see. One is, of course, caused by planetary curvature, your ability to see in the distance from the surface of a planet or a moon is governed by the size of that world. There's another type of limitation or horizon, which we would call an optical horizon, and that's a horizon that's produced by the limit of the human eye, what the human eye can detect in terms of number of photons it's receiving, either with or without optical aid. And the third and final kind of limitation on how far we can see has to do with the fact that we live in an expanding universe and we are limited by the speed of light, and that governs or limits rather how far we can see at cosmological distances, and we'll be talking about all of that. So let's start first of all with the physical horizons. These are kind of easy and fun. First of all, let me define what a horizon is on a world. It's simply where your line of sight intersects a perpendicular to the center of the Earth, as you can see here. This person is looking out perhaps over the ocean and sees a line in the ocean that you saw in the previous slide there. And that's the point that intersects a perpendicular to the center of the Earth at a right angle. Obviously, how high you are above the surface governs how far that horizon is from you. And there's a very simple formula you might want to remember. You take your height in meters over the surface of a world and multiply it by 13 and take the square root, and that will give you the number of kilometers to that horizon, just the square root of 13 times the height in meters, little rule of thumb. So if you're standing on a beach and you're, let's say, 5 feet tall and you're standing a foot above the sea level, or you're perhaps 6 feet tall and standing with your toes in the water, that line you see out there is about 3.1 miles away. And what that means is that if someone were standing on a platform at the water's surface 6.2 miles away, that person would be completely hidden from you because of the curvature of the Earth. On the moon, that horizon is much closer. The horizon you would have standing on the surface of the moon would be 1.5 miles away, somewhat further if you're up in the LEM looking out the window. If you're 100 feet up, that horizon, if on a clear day, would be about 12 miles, unless, of course, you're seeing mountains in the distance. They would have stick up and you'd see further in that case. If you went to the top of the Burj Khalifa at 2,700 feet, on a clear day, you would see a watery horizon 64 miles away. And from the top of Mount Everest, the horizon would be 264 miles away, unless, again, you could see the top of, say, Kanchenjunga, in which case you could see well over 300 because it would stick up above the horizon, the true horizon. One time I was sitting in my office and I was looking out over the east end of Louisville, and I just had this thought that I wonder how fast the Earth drops away under me. In other words, what if I were standing on a steel plate, a perfectly solid steel plate that just extended out over for many miles in all directions? And if I walked out on that plate 1 mile, how far beneath me would the Earth have dropped because of the curvature? And the answer is 8 inches. 5 miles, 17 feet. 10 miles out to where I lived, it was actually 67 feet lower than the steel plate on which I would have been standing in that case. And this continues, if you, for example, imagine yourself standing at one side of the United States on a steel plate, the other side would be about 789 miles below that plate. And if you move out 4,000 miles, then you miss the Earth entirely, of course, so it ceases to have any meaning at that point. The drop's about 8 inches per mile squared, if you want another rule of thumb on how much of a drop there is because of Earth's curvature. And Earth's curvature is not something that you can only see if you're flying in a U-2 or in a space capsule. You can see it from the surface of the Earth if you know where and how to do it. Being in the ocean on a clear day and putting your mouth in the water so your eyes are just barely above the surface and watching a ship in the distance, you'll see that ship disappear, but only partially at times. In this case, you can see the sails of a ship, but not the body of it. Lake Pontchartrain is a wonderful place to observe this phenomenon because they have power lines that cross the lake. And you can see literally the curvature here from these power lines. If the Earth were flat, the top of those power lines would extend in a straight line to a horizon that would be 288 feet higher at a distance of 23.8 miles. So it is visible there. There's also an experiment you can do out here at the Bonneville Salt Flats. This, of course, is a perfectly conformal surface to the curvature of the Earth because it's a dried lake bed, and the salt left over is just perfectly conformal to the surface of the sphere of the Earth. And so what you can do is place a flashlight on the surface and move away 1 mile and get down below about 9 inches above the surface, and the curvature will actually block your view of that light. If you raise your head up about 9 or 10 inches, you'll see the light shining at you. Well, now we turn to optical horizons. How far can we see based on how many photons we're receiving? Well, let's start with the naked eye. We know that a 100-watt light bulb puts out about 300 quintillion photons per second. So photons come in large numbers from objects that we regard as routine. An experiment was done at Texas A&M some years ago to see how far away, looking through the atmosphere, we could see a candle. And the candle was detected at a distance of 1.6 miles and was deemed to be the equivalent of roughly a magnitude 6.0 plus 6 star. This flux amounted to approximately 2,700 photons per second entering a fully dilated 7-millimeter wide pupil. However, looking up in the sky through less atmosphere, if we get completely away from any form of light pollution, perhaps in the middle of the Pacific, and look up, a magnitude plus 8.5 star can be seen with the naked eye, but you have to eliminate all extraneous light. If you can see a magnitude plus 8.5 star, the flux is about 270 photons per second being accumulated through a 7 mm wide, fully dilated pupil. Of course, age affects this. As we get older, that maximum pupillary diameter can get smaller. I had an experience. I spent a lot of time at Patoka Lake. In fact, I've done about 68 all-nighters there in the last 2.5 years, so I feel like I should be paying taxes in Indiana. And one night, and this sketch did not come through on the copier. It's just way too contrasty in this image, but you'll get the idea. I was looking for this galaxy, NGC 499. And when I was observing it, I noticed a little smudge over to the right that I wasn't expecting. And so I looked at the guide that I happened to have with me, and it said, look for NGC 496 in the same field. And so as I was sketching, I was jiggling the field a little bit to get some field motion to help the averted vision a little bit. And I noticed an incredibly faint smudge that was clearly moving with them right in between. So I just sketched it in and went home and looked it up later. And it turned out to be NGC 498 that had this magnitude listed for it. And so I decided to try to determine how many photons I was receiving from this little beast. So we know a 0 magnitude star produces about 500,000 photons per second for every square centimeter of surface area on the Earth. In other words, if you have a 0 magnitude star shining up above, like Vega, for example, on a sheet of paper, 1 square centimeter, about 500,000 photons per second will be hitting that square centimeter from Vega. A 12-inch SCT minus its obstruction has about 826 centimeters squared. So I was getting about 413 million photons per second collected. But that would be from a 0 magnitude star. This was plus 16. So we have to divide by the difference in magnitude of 16 magnitudes, which is a factor of 2.512 million. So that cuts it down to 172 photons. Then you've got the glass transmission factor, 80%, extinction of the atmosphere at 50 degrees, reduces it to 105 photons. Corneal transmission, you lose a few percent as a result of corneal transmission. And then there's the integration rate of the eye, the temporal accumulation of information that's sent to the brain, which is roughly equivalent to 1/5 of a second. So I was seeing something that was actually producing approximately 18 photons per integration period. That's how little you can see, how few photons can actually be detected by the human eye. And this experiment's been taken even further. Alapasha Vaziri at Rockefeller University set up a very complicated device to try to determine if the human being, a human eye, was actually able to detect a single photon. And the individual was placed in a completely dark room, was given a button to press, either yes or no, and was asked to stare at a fixation light. From the side, this complicated device would, in some cases, fire a single photon in at an angle to the eye, toward peripheral vision where it would be more likely to be detected. And what happened was they did thousands and thousands of tests, and there would be a sound issued, a bell, if you will, and then an ending sound. And during that time, the person had to determine whether a photon had been detected or not, yes or no. And the way they did it with the 0, that is when no photon was emitted, they got a positive response approximately 52% of the time. However, when a photon was actually fired, they got a positive response about 60% of the time, which was deemed to be statistically significant for the human eye and brain detecting a single photon hitting in peripheral vision. There have been some other scientists who have challenged this. They think that perhaps it's not statistically significant. Others say 10 photons is the minimum, but nonetheless, Dr. Vaziri concluded that 1 photon could be detected. So how far can we see with the unaided eye? The furthest star you can see with the unaided eye is V762 Cassiopeia. It's magnitude plus 5.8 at 16,308 light years. However, we've seen stars at further distances. Back in 1885, there was a supernova in Andromeda. the supernova reached approximately magnitude 5 and was visible, therefore, at a distance of 2.5 million light years to the human eye. But that's hardly the record. The record occurred on March 19th, 2008. A gamma ray burster occurred in Boötes. It reached magnitude 5.5 and was above magnitude 6 for about 30 seconds. And this light was coming from a gamma ray burster at a distance of 7.5 billion light years, visible to the unaided eye. Here's the light curve for it. So you can see it reached the naked eye visibility up here for approximately 30 to 40 seconds. If you'd been looking in the right place, it's not likely you would have exceeded that. This young man's name is Scott Harrington. When he was 14 years old, he undertook a project with the limited optical equipment he had on his farm in Evening Shade, Arkansas. He started off with 7x35 binoculars and published online the results of a 14-year study, or actually, an 11-year study that was trying to determine what was visible to the unaided eye and what was visible in 7x35 binoculars. He determined that over 250 deep sky objects were visible with 7x35 binoculars, and also a number of things you wouldn't have imagined possible to see with the unaided eye as well. Based on his research, and by the way, the cover of the new issue of Sky and Telescope magazine features an article he just wrote for Sky and Telescope, so you might want to look for that this coming month. He determined that the furthest open cluster visible to the unaided eye was the double cluster, NGC 884 component to be exact, at 9,580 light years. The furthest emission nebula visible, the Swan Nebula, at 5,900 light years, again, naked eye. The furthest globular cluster, M2 in Aquarius, plus 6.5 magnitude at 37,500 light years. And naked eye visibility can detect M81 in Ursa Major at 11 million light years under ideal conditions. Now you move to binoculars and suddenly the range gets much further. For example, and I won't cover all the different objects, but he was able to detect NGC 3607 in Leo at a distance of nearly 70 million light years with just 7x35 binoculars. With amateur telescopes, and by the way, Scott is now using a 10-inch and some other much more sophisticated equipment and has managed to observe 2/3 of the Herschel 400 catalog with 8x56 binoculars or less. With amateur telescopes, the range is much more incredible. 3C273 in Virgo, I'm sure is a target many of you have looked at. Very, very accessible to amateur telescopes. Magnitude plus 12.9 lies at a distance of 2.44 billion light years and is for most amateurs the furthest thing they've ever seen. This is an object that if we brought it as close as Arcturus, it would shine at this brightness level. That's how 3C273 would look if it were 36 light years away from us. But there's something further that's visible. If you have a Dob, you know how to search for quasars that are extremely faint. You might want to look for this little red thing right here. This is APM 0827952555 in Lynx, and it shines from a distance of 12 billion light years. You're looking almost to the beginning of time here. If that were moved to the distance of Arcturus, and you might want to squint just a little bit right now, it would shine at magnitude minus 45, about 16 million times brighter than the sun from Arcturus's distance. With professional telescopes, however, with the great telescopes in Chile and Mauna Kea, we can detect even further galaxies, including this record holder that I'm going to be talking about in a few minutes. So I want you to pay particular attention to this. What you're seeing here is a highly enlarged, pixelized image of a little tiny red dot on this deep field image of the Hubble Space Telescope. The galaxy is called GNZ11. It's very tiny, only 600 light years wide, and shines at us at a distance, light travel distance of 13.4 billion light years. Now our universe is 13.8 billion years old. So you're seeing an object here that sent its light to us just 4/10 of a billion years after the Big Bang itself. This is the record holder currently, the furthest galaxy we've ever imaged. It is merely a proto-galaxy. It's bright white stars, blue-white stars that look heavily reddened because the light from these stars has been traveling through expanding space so long that the light has been stretched 11 times longer than its original wavelength, hence the Z11 in the name of the galaxy. It's a little proto-galaxy. This is a first-generation galaxy. Stars had just formed for the first time from the dark age after the universe became transparent, and now began glomming together to form this little proto-galaxy. Later, proto-galaxies would be joining together to form larger and larger galaxies later in time. The James Webb Telescope, if you've noticed, its mirror looks yellow. It's because it will be concentrating on looking at these early galaxies that are heavily reddened. And so the mirror is highly sensitive to infrared light, which will make it very good at studying galaxies like this. So keep GNZ11 in mind. Its light took 13.4 billion years to get here. We'll be talking about it a little bit more in a moment. There is some further light. The cosmic microwave background, the heat left over from the Big Bang, which has been stretched into the microwave, shines at us from a light travel distance that goes back to the very beginning of time itself. The point about 380,000 years after the Big Bang, when the universe was still opaque, we see that opacity as if it still existed, which of course it doesn't. Well, this takes us to the question of cosmic horizons. Now, what we're talking about now is horizons that are produced by the limitations of the speed of light in an expanding universe. And so there are a couple of little preliminaries that I need to cover in order for this to make a lot of good sense. The first of those is that, of course, the universe is expanding. This expansion rate is called the Hubble Constant, which is a misnomer because it's not a constant. It's a constant everywhere in space at a given time, but it's certainly changed over time. When the universe was about 1 billion years old, the universe was expanding 10 times faster than it is today. The current rate of expansion is believed to be somewhere between 67 and 74 kilometers per second for every megaparsec of separation between 2 points. Now, a megaparsec is a little bit further than the distance between the Milky Way and Andromeda. So if you have 2 points that far apart, the expansion of space will carry them apart at about roughly 70 kilometers per second. Another way to think of this is for every 1 million light years of separation, you have about 48,000 miles per hour of separation. Or if you have 1 billion light years of separation between 2 points, 48 million miles per hour. That's about 1/14 the speed of light, which takes us to the next point, and that is that if you have 2 points that are about 14 billion light years apart, those points will be carried apart by the expansion of space at the speed of light. Galaxies further than 14.4 billion light years will be receding, or not receding, but separating from us at greater than the speed of light. This does not violate special relativity. Nothing's moving through space faster than the speed of light. Nothing's being observed moving faster than the speed of light. It's just the expansion of space itself that is carrying points apart. This distance at which points are being carried away from us at the speed of light is called the Hubble distance, and that's 14.4 billion light years in all directions. Next thing to understand is what I alluded to a moment ago, and that is that the universe expansion has not been constant over time. For the first 8 billion years, the rate of expansion slowed down as matter acted like a gravitational brake on the expansion. But about 6 billion years ago, that changed. Matter became more attenuated, and now, because of what we believe dark energy is doing, the universe expansion is accelerating. It's getting faster and faster today. That's the result of some recent Nobel Prize-winning work. And finally, the expansion of the universe and the accelerating expansion that we see today and the speed of light make distances harder to understand. So let's revisit for a moment how that's so. Here we have GNZ11. How far away is it? Well, one possible answer is 1 billion light years, because that's how far away we were from it when these photons that you see in this image left there. Okay, so we're a billion light years away, and the photons begin their journey toward us, but the universe is expanding, and so they have to catch up. We're moving away from GNZ11 and they from us because of this expansion. So the photons end up having to swim further, if you will, to get to us. And they take 13.4 billion years to get here. So we could say it's 13.4 billion light years away. Except that's not really true either, because the entire time those photons were traveling to us, the expansion carried GNZ11 to a distance of 32 billion light years, which is where it is today. Now, let's review that in different terms. Let's imagine that we have a swimming pool. All right, here we have a father teaching his daughter to swim. He's already told his daughter how to do the crawl and kick her feet. And she's wearing a yellow swimsuit because she's going to be our photon. And the wall she's hanging onto is going to be G11, GNZ11. And Dad, that's going to be us. Now, when my dad taught me to swim, he tricked me and he backed up the whole time I was swimming to him. But this dad's not going to do that. He's just going to stand in this pool 10 feet away and the daughter's going to swim to him. But this is a magic swimming pool. It expands constantly and extra water is pumped in to keep the depth up. And so she lets go of the wall and begins swimming to Dad. She's making progress, but by the time she gets to Dad, she's ended up having to swim 100 feet. And even more amazing, when she turns and looks back at the wall, she finds that the wall is 300 feet behind her. This is GNZ11. We were a billion light years away when the photons left the wall. The photons had to swim 13.4 billion light years, or 100 feet, to get to us. And by the time they did, the galaxy had receded to 32 billion light years away. Now, none of these distances is really very satisfactory. And this is what makes talking about distance so difficult. If we say it's a billion light years away, then we have to wonder why the light took 13.4 billion years to get here. If we say it's 13.4 billion light years away, well, that's fine. But if we were able magically to transport ourselves back up the light path 13.4 billion years instantaneously, we wouldn't find the galaxy there at all. It's 32 billion light years away. And if we talk about GNZ11 being 32 billion light years away, well, we have to wonder how the light ever got here in 13.4 billion years from such a distance. Plus, we also know that any event that occurs today on GNZ11, we're never going to see, no matter how many trillion years we wait in the future. Because if the daughter tried to turn and swim back to the wall now, there's so much water expanding, she can never reach GNZ11 again. She can never get back to the wall. Nor can another swimmer, perhaps the father's son, nor can he manage to get to Dad at this point. There's simply too much water expanding at the same rate. And so that's the problem of distance that is imposed by the speed of light in an expanding universe. Now, I'd like to show you something here that kind of defines what these horizons are. And this is how we'll conclude. This light area in here is simply the distance from which light has had time to reach us. It's 13.8 billion light years in radius. That's how far light has been able to travel. That's the age of the universe. Light, let's say, coming from a point 15 or 16 billion light years away hasn't had enough time to get here. Here's that Hubble distance. That's the point that's moving away where we're being separated from it by the speed of light. Okay, ignore this one for a moment. Just pay attention to these two. So let's plot GNZ11. We know its light travel time, that the light traveled 13.4 billion years to get to us. And by the time it got here, the galaxy had retreated out here to 32 billion light years. And that's the furthest galaxy we've ever observed. There are lots of other galaxies, all of which are closer, about 2 trillion of them. Most of those galaxies lie way out here. Obviously, the further out in space you go, the more volume there is and the more galaxies there are, as evidenced by the Hubble Deep Field. Now, what if there had been a galaxy in existence the minute the universe became transparent 13.8 billion years ago? that light would have had time to reach us. And if there had been such a galaxy, we would know that today that galaxy would be out here at 46 billion light years. That's why we call it the cosmic horizon, the cosmic particle horizon, or as astronomers refer to it, the edge of the observable universe. 46 billion light years is the location today of the furthest things that we can see already. If there had been a galaxy in existence at 13.8 billion light years distance, that light would have had time to reach us by now, and we would know that today it's actually at 46. And so this is the edge of the observable universe. Now that's old light that we're talking about. So let's refocus for a moment and think about new light. What if we have a galaxy here at 15 billion light years? This is where it is today. Can we see this galaxy? Sure. We can see this one, right? We can see GNZ 11. It's out at 32 today. So this one at 15 today undoubtedly sent light to us long ago when it was in here somewhere, and today it's out at 15. But what if a supernova occurs in this galaxy today? Will we ever see it? Notice that it's beyond the Hubble distance. This galaxy and we are separating it faster than the speed of light. Will we ever see the light from that supernova? It seems like the answer should be no. But in actuality, if those photons can somehow make it inside that Hubble distance, they'll make it the rest of the way eventually. And the distance between the galaxy and the Hubble distance here is not expanding faster than the speed of light. So those photons will make it to the Hubble distance, and they'll make it on in to us eventually. It hasn't had time to get here yet, but eventually we'll see that supernova that occurs today. That's true out to a distance of 16 billion light years. At 16, the photons can just barely make it to our Hubble distance and will make it on in. Beyond 16 though, there's simply too much space between that galaxy and the Hubble distance that's expanding too fast, and the photons can never make it. And that creates what we call a cosmic event horizon at 16 billion light years. Don't get confused by this. This is simply the distance from which an event occurring today can eventually be seen by us. Anything occurring beyond 16 billion light years, we will never see. So for example, if a supernova goes off in GNZ 11 up here today, we're never going to see it. You can wait 1 trillion years, you can wait 1 quadrillion years. The light will never reach us. If an event does occur at 16 billion light years, and that light eventually reaches us, we will know when it reaches us that that galaxy that hosted that event is actually out here at 62 billion light years. It's very similar to this pair up here, only in this case, we're talking about today light. A supernova occurring at 16 billion light years will eventually reach us, and when it does, we will know that that supernova and its galaxy are actually at 62 billion light years. That's the absolute limit. That's the future visibility horizon. It is the distance of the furthest things that we will ever see when we see them, but we don't see them yet. Now, I know that's all amazing, but consider this for a moment. Everything beyond 16 billion light years is unreachable. That means that no object, including all of these billions of galaxies that lie beyond 16 billion light years today, they cannot get light to us anymore. They cannot send a signal to us anymore, nor we to them. The pool is simply too large. It's like the daughter who tries to turn around and swim back to the wall. It's too far away and there's too much water expanding. This means that 96.7% of the galaxies that we see now, such as in this picture, are already unreachable. We can't get a signal to them. They can't get a signal to us. The last photons that will ever reach us from these galaxies left there long ago. Those photons are still streaming in, but we're not going to get any new ones. And 98.6% of galaxies that we will ever see in the future are unreachable. What lies beyond these horizons? Well, that depends, of course, on the shape of the universe, whether it's curved and closed or open. Studies indicate at Oxford University and from, of course, the Planck, Cova, and WMAP satellites that our universe is flat with an error of about 0.4%. And just to simplify this, I'll tell you what that means. It means that if the universe tests flat with an error of 4 parts in 1,000, then the universe could be curved, but undetectable if it's at least 250 times larger than the part we can see. That would be a volume of 15.6 million times larger than the part we can see. And that's where we leave it. The universe in which we exist lies vastly larger than the part we can see out to our cosmic horizon at 46 billion light years. The Oxford study says 15 million times larger. Alan Guth, the originating particle physicist who came up with inflation theory, says 300 sextillion times larger by his calculations. Andre Linde calculated 10 to the 40,000th power times larger than the part we can see out to 46 billion light years. So that's a little extensive hint of the types of horizons that affect how far we can see. I realize the last part there is a little bit daunting, a little bit difficult to comprehend, but I thought I would just give you an idea of how big things are and what the limits are and how far we can see. So if you have any questions at all, please have at it.
Now I've got a headache.
I get that a lot. I'm sorry, but it's an area that it's fascinating to me, and it has taken many years to get used to this. I've got the advantage of a good friend at Princeton who's an astrophysicist who's helped me through some of the rough spots on this. But basically, there are just some distances beyond which communication can't occur anymore, and limits what we can see. And by the way, those horizons are actually moving in on us a little bit, because as the universe expands faster and faster, the distance from which things can reach us gets closer and closer to us. So it's closing in on us over time.
So you think the movie Passenger is you think the movie Passenger is a good one to watch and take some hints from? Is that how we might travel intergalactically?
Well, you know, intergalactic travel is theoretically possible. I remember reading a Time magazine article one time that talked about the fact that if you could simply accelerate a spacecraft at 1G for 1 year, and then drift for about 20 years, and then turn it around and fire your engine at 1G to slow down for 1 year, you could cover 35 million light years in roughly 24, 25 years of shipboard time. That's just relativity, and it works. The trouble is, you don't want to hit sand grains going at 99% the speed of light. You're going to need about 250 pounds of fuel for every 1 pound of spacecraft. So you have to collect fuel and hope you can continue collecting fuel en route. And the accuracy of where you end up, I mean, even if you were able to get close to your target over that distance in that much time, what good would it do? In other words, if you just found yourself in the middle of a galaxy, what are the odds you'd be within any reasonable distance of something within that galaxy? You'd be 2, 3, 4 light years away from something. So it's impractical for a variety of reasons. It's an engineering nightmare. It's merely scientifically possible.
Yeah, right. So I guess we better stay in our galactic neighborhood then.
Probably, yeah. I think so.
I had a question about some terms you used I wasn't familiar with. You mentioned opaque and then transparent universe.
Yes.
Can you explain that a little?
Sure. It's thought that the universe at about 10 to the minus 37 seconds, excuse me, the first like undecillionth of a second of the universe, that the universe was very tiny, incredibly tiny. And that during that time, the universe was able to trade information about its temperature, reach equilibrium, if you will. And then during the next undecillionth of a second, it inflated dramatically because of gravitational repulsion. And I'm not going to get into all that, but basically in the first undecillionth of a second, the universe inflated to enormous size. And then that inflation energy decayed and filled the universe with hot plasma, which we call the Big Bang. It was not actually the first moment of the universe. It was sort of the third moment of the universe, but within an undecillionth of a second of the beginning. So this universe is now filled with hot plasma. The universe is expanding, the hot plasma is getting thinner, but while it's filled with this hot plasma, photons can't travel through it. They hit other nuclei and they get absorbed and then re-emitted, and they get absorbed and re-emitted, something similar to what happens deep in the sun. But as the universe expanded, this became thinner and thinner. And about 380,000 years after the Big Bang, it suddenly became thin enough that the universe everywhere became transparent. And so light, now the photons can travel through space. This is the beginning of kind of a dark era. There was gas in this universe, but no stars had formed. So we went about 400 million years before stars began to collect from this gas and began to glom together to form little proto-galaxies like you saw GNZ11. So that moment of transparency occurred about 380,000 years after the Big Bang. And because when we look out in space, we don't see the present, we're looking back in time. If we look back far enough with our satellites, we can see that hot plasma. It's almost like it's a bubble around us of hot plasma that lies at a distance of 13.8 billion light years. It's not really there now. We're looking back in time, so it appears to be there. And that's that cosmic microwave background that you saw, that modeled image that I showed earlier.
Oh, okay. Thank you.
So Chuck, I haven't given a lot of time to contemplating this, but beyond the 13.8 boundary, what is out there? I mean, you pointed out a few very, very early galaxies and so forth, but if space is expanding, what's expanding actually?
Okay, first of all, those early galaxies don't exist now.
Okay, because they're
okay. If GNZ11 were looking at us now, they'd see a little tiny proto-galaxy also. Okay, you're looking back in time at GNZ11. All right, and it's only time that limits how far we can see there. Essentially, the universe is filled with galaxies, just like we see, only it's much larger volume than we can see. And we can never look out and see galaxies as they are today. We're always looking back in time at how they used to be. This is what makes it so difficult to comprehend. So basically, if you look at your local galactic neighborhood, you look at M51, M101, the Virgo cluster, and so forth, that's what exists everywhere. It's this cosmic web of filaments of galaxies filling space. And it's vastly larger than the part we can see out to 46 billion light years. 46 billion light years is where things are today that are the furthest things that we can possibly see right now. But beyond that is much larger volume of the same. Did I answer your question? I'm not sure if I reached all of it.
Yeah, I think you started.
Chuck, it has been said that we have the 5 giant galaxies 800 million years after the Big Bang. How can that be? They didn't have time to form.
It's simply possible. I mean, we're not finding a lot of them that far back. Mostly, you have very tiny galaxies forming about 400 million years, about 0.4 of a billion. But the rate at which they collect has to do with anomalies in the location of gas. If there was a lot of gas in one particular area, larger proto-galaxies could form and advance more quickly. It's not uniform in that sense.
The farther away you get from your object, does that mean if you're traveling at high speed, somewhere near speed of light, does that mean you can see farther to the earliest? 'Cause you
I'm
move
sorry,
farther?
I missed the first part of your question. Can you start over?
Yeah, so if somebody's in a spaceship, say, and they leave the Earth and they're traveling at a high speed, as they get to that place where maybe the galaxy was, can you now see the light from a further distance because you moved, or you never get there because
No,
I see, because
no.
everything's moving.
Every viewpoint's the same in the universe. Everyone sees the same thing.
So
Everyone has the same horizons. We have horizons around us. Some point over here in space has horizons around it, the same horizons, governed by the same expansion rate.
but wouldn't they be different horizons based upon how
Sure.
far they are?
Sure.
And there'd be intersections of horizons too? Like,
Well, we see GNZ11 at this enormous distance, okay? They can see things 13.4 billion light years on the other side of them that we can't see because it had no
Right.
time to reach us. And we're at the limit of what they can see, even though we can see.
Can't hear you. Did it get unplugged?
Think so.
Yeah, I think he became unplugged.
Beyond the Hubble limit, I think.
he's in another horizon. An audio horizon.
The acoustic version.
Yeah.
Coming.
Cosmic disconnect.
I'm gonna come back, so keep an eye on the waiting room, Jim.
That was pretty fascinating. I never even considered what he was saying. I never even thought about that.
No. I think I'm with Dick. My head hurts a little bit thinking all that hard.
Damn hard to understand.
Yes, you need some of that supercomputing power.
I'd like to know what lake he was at again. I didn't catch the name.
I think
Patoka, Lake Patoka.
Where's that?
Southern Indiana, isn't it?
I know that, but
yeah,
where?
it's that one. There you go.
I think it was
Is that
near.
a Brown County Lake or
I
what?
think it was
That's
near
not too far from Evansville.
Just state park.
Oh, is
yeah,
it?
near NGC 784.
Take a left.
man.
That's quite a ways from Louisville.
Oh, here we go. He's back.
Bring him in.
Chuck.
Yes, he's back.
Welcome back.
Can you hear me now?
Yes.
Yeah.
Good. Sorry about that. I yanked the microphone out of the computer. And it always switches to some other microphone, and I don't know which one how to get back. Okay. I'm sorry. Where were we?
Before we go any further and before we lose you again, thank you very much.
Well, I appreciate it. Thank you.
Yeah.
And again, I like to give programs like this mostly just to get people interested in something. You know, it's not something that's easy to grasp at first. It takes time. It took me time. But there's some fascination to it all. And hopefully that triggers some interest. And there's some good books I can recommend on it too.
It's good exercise for the imagination.
Yeah.
Chuck, I got a question.
Yes, sir.
So you said something fascinated me. I guess you were answering a question and mentioned it. So going out 13.8 billion light years, you'd mentioned if they were to turn around and keep looking further out, they would see basically the same thing as we're seeing, you know. They would see a horizon themselves for almost 14 billion. So how far out, and I know this is the wrong term, but you know, because there's, I mean, using a term like if you were to keep continuing to go out in a linear line, moving out in distance, are we going to just go out indefinitely and everybody would be able to see 14 billion light years further and further out, everybody?
Well, if you're asking about an edge to the universe, there isn't one. And part of this has to do with the effect that time has as a dimension. If you were 50 years old and you were 50 light years tall and you look down at your feet wouldn't look the way they do to you now. You'd have little baby feet that you were seeing. When you factor time on the large scale into things, it alters what you see. The universe is not expanding into anything, although inflationary cosmologists will tell you that we live in a bubble universe that's a bit of true vacuum that has formed in the middle of an expanding sea of false vacuum. You'll read all about that in these books on inflation. But essentially, I mean, there's no edge to it. The universe we live in is all of space and time. It's simply everything. There's no wall. If there was a wall, you'd have to ask, well, what's on the other side of the wall? That would be a defined place. And so that would have to be part of your universe as well. And so the geometry of the universe is a little bit strange. It's a little bit hard to comprehend, really, for most people, and for me too. but
at any given instant, if you were to go out 14 billion light years out and that person out there turned around in the opposite direction, they would see things 14 billion light years past them.
Yeah, I mean, you just carry your horizons with you wherever you go.
Yeah, so I guess
I have a question also. And the question is, as far, considering that as you approach the speed of light, time for you seems to stand still.
No, not for you, it doesn't.
Not for me, but for as far as all the observers.
Yeah.
Is it right to think that as far as photons are concerned, all other photons everywhere that ever exist from the beginning of time are all one event?
There was actually a scientist who postulated once that maybe there's only one photon in the entire universe.
Yeah.
Because photons don't experience time because they're moving
That's
at the speed of light. And so that one photon has the time to be everywhere, to take the place of every photon in the universe. I don't think that's gained much traction. In fact, I know it hasn't, but it was just idly postulated by an astrophysicist one time as a matter of interest. I don't think that's worthy of consideration, but it is true that a photon experiences no time transmitting over long distance.
Yeah, I have a question.
Yes.
Is the universe infinite or finite? And I don't understand also how we can see the relics of the Big Bang explosion in the cosmic background now, but we can't see the whole rest of parts of the universe. So that's two parts.
Okay, the question of whether the universe is infinite or not is no one can answer yet. I mean, what we're trying to do is determine if the universe is flat or curved, positively or negatively. Right now, it seems to be flat. All the studies from the Cova and WMAP and Planck satellites have it flat, which seems unlikely because it's teetering on the edge of a razor blade. You know, the fact that it could be so precisely balanced as to be flat. If it's positively curved, then it's finite. If it's negatively curved, it's infinite. If it is flat, then it expands and stops at an infinite point in the future. So likely infinite in that sense, yes.
You could travel.
So how do we?
You can't circumnavigate it. If you could travel at the speed of light in one direction, you're never going to circumnavigate the universe.
Okay.
I just didn't understand how we could not see parts of the universe, but we can detect the Big Bang radiation that happened at kind of like time zero. So it seems like everything that there is should have been in that little pinhead that blew up, and therefore how can I see the radiation, but I can't see all the rest of the stuff?
Well, that's the factor of time. When we're talking about the fact that there are galaxies a trillion light years away, we're talking about right now. When you're talking about seeing the light from the microwave radiation from the Big Bang, we're talking about looking back in time, which is the only way we can look. So when you look out at the cosmic microwave background, when you look at anything, when you look at the moon, you're looking back in time, a second, a quarter. Okay, so when you look back in time, which is the only way we can look, you will see this radiation from the Big Bang. That's past. But the current, right now, there are galaxies far, far away beyond that.
Okay, thanks.
Whose light has not had the time to reach us yet. And as time passes, where we see that cosmic microwave background gets further and further from us. In other words, if we wait 1 billion years, we'll be looking back 14.8 billion years, light years, to the cosmic microwave background, because we can't look any further back in time than that.
So
time is the problem here.
Yeah.
You know, you have a universe that exists, but wherever you are, you're limited by how far back in time you can look, and that's what these horizons are about.
I have a question on the photon collection.
Yes.
You had an interesting fact that I'd never heard before. You said the corneal transfer rate is about 0.87, which means we lose about 13% of the light through our corneas then, right?
It's just reflected light off of it. Mm-hmm.
Right. And then for people who have implants and other issues, you'd probably even higher perhaps.
Sure.
In the side. Secondly,
the implant probably helps a little bit. I mean,
yeah.
Cataract, yeah.
Yeah, clarity versus for collecting photons when you're looking at galaxies and stuff in astrophotography, no matter how many hours of data accumulation you have, whatever like that, you always have the little the stars, kind of the bloated stars around the edge and everything else. But the center disk is always just a fog. But that's where masses of zillions of stars or whatever is like that. Shouldn't the photon density overcome and give more? What's happening there that you don't get the, you see where I'm going, the thing that you can always show the edge, they show the crispy toast on the edge there, the dust lanes and stuff like that. But the center part of that, where the mass or the meat of the galaxy is just always shown as a fog.
What's the question?
Why are we not getting the incredible light densities that would be emanating from the main part of the galaxies? Why are we just picking up the outer edges?
Well, I don't think we are just picking up the outer edges. I mean, visually, what you see mostly is the nucleus of the galaxy.
But there's no resolution to it. It's just
no.
Okay.
Yeah, it's far too far away to resolve anything. I mean, even in the spiral arms, you're not resolving anything visually when you look at a galaxy. If you're lucky to see spiral arms using a large Dob, for example, I mean, you're still seeing a fog in the form of a spiral arm. You're not resolving anything. The large telescopes can begin to resolve some stars in close galaxies. But, I'm not sure how to answer that.
Are you saying that every object is moving away in 360 degrees? Like some objects were moving away from other objects?
No, and I should have emphasized this. And that's an important point. I'm glad you raised it. The expansion of the universe, as I pointed out, for every 1 million light years of distance, 48,000 miles per hour. That does not apply in gravitationally bound systems. The distance between your childhood home and your high school has not changed. The Earth is not getting bigger. The solar system's not getting bigger, the Milky Way's not getting bigger, and in fact, Andromeda and the Milky Way are moving toward each other and will collide. These are all gravitationally bound systems, and that overcomes the expansion. But when you get into the spaces between galaxy clusters and in the voids among the filaments of galaxies, that's where the expansion takes place. So it's something that definitely affects your ability to talk about distances in the billions of light years. But when you're talking about the local group of galaxies, for example, the expansion won't play a factor at all.
Hey, Chuck, I got it. Oops.
How far away or how fast C3273 is moving away from us right now?
I don't know. That's at a distance, however, where it's much closer than GNZ11, okay? And so you're talking about 2 billion light years. So the differences in how far away it was when the light left there and where it is now and the light travel time is not that great. So we might have been 2 billion light years away when the light left there. The light travel time may be 2.4 billion light years, and maybe today it's a 2.6. It's a small range because it's closer, and so those pool distances in the example are not as dramatic.
Can we determine how fast it is moving away from us?
Sure. Yeah, by its spectrum. Look for its redshift.
Okay.
I just don't off the top of my head know what that is.
Hey, Chuck, I have another question from one of the members.
Yes.
Let me read this. Ward Price is asking, if the universe is expanding and 13 billion years ago it went through inflation, that sounds like the universe used to be smaller than it is today. That sounds like the position we inhabit in the now was at one time not in the universe. In other words, outside the universe or outside the outer wall of the universe, which does not exist, then why not? I'm not sure I totally understand it, but that's the question.
Okay, well, first of all, there's no wall.
Yeah.
All right, the universe is, there's this idea that the Big Bang that you see all the time in videos, that the Big Bang is depicted as an explosion, like a firecracker going off in some room. That's not it at all. It's the creation of the room. It's the creation of space and time itself is what the Big Bang was. And it was actually the moment at which the inflation stopped and all the energy that was this dramatic energy that inflated the universe 100 doublings in size in about an undecillionth of a second, that energy had to go somewhere, and it filled the volume of the universe with hot plasma. So there's no wall out there. There's no edge to it that you could ever find or detect. And part of that's because we're embedded in a dimension in which we can't move. If I can give you an example, imagine that you had a flatlander living on a flat plane universe. And the flatlander thinks, okay, this universe is infinite because it's perfectly flat, so I should be able to go forever in one direction and just keep going. And so flatlander stick figure travels west and keeps going and ends up returning home from the east. And now concludes that actually his flat universe is part of a giant sphere that is so big that it seems perfectly flat to him, as our universe does to us. Okay, but from this, the flatlander now concludes that my universe is unbounded. I never ran into an edge, but it's finite in volume. It's finite in size. It's the surface of a sphere. Similarly, we are three-dimensional creatures, and we're embedded in a dimension of which we can't move. We can't move in time. We can't go back in the past or into the future. And so this gives us the possibility that we live in a universe that is finite in volume, but unbounded in a similar sense.
So Chuck, the getting back to the expanding universe. So the concept of the universe being kind of like a balloon, expanding, growing larger in volume is totally incorrect.
Well, it's incorrect if you picture the interior of the balloon as the universe. Those images of the balloon analogy, it's the surface that represents the universe, not the interior. The interior is the past. It's the center of the balloon is the Big Bang. It's a point in the past. The surface of the universe, the surface of the balloon rather, represents the volume of the universe, just the surface in that analogy.
So we exist on the surface of that
Only on the
expanding
surface.
balloon.
It doesn't satisfy because it's hard to imagine the surface of a balloon as a volume. Okay, it's an infinitely thin, surface, but it's just an analogy. It shows you why every dot on the balloon appears to be receding from every other dot. And a better analogy is sticking raisins on the balloon, because the raisins won't get bigger as the balloon expands. They're gravitationally bound. The expansion doesn't affect them, but the raisins get carried further and further apart as the balloon expands. That would be the best way to think about it. But it's just an analogy.
Yeah, right.
Has to increase with the expansion of the universe.
What has to increase?
Dark energy. The dark energy, the stuff that's making the universe expand,
Yes.
has to increase as the volume of the universe increases. Where does that energy come from?
That's the magic. That's the magic trick. The true vacuum of space is full of energy. It's full of Higgs field, full of dark energy. And there's a constant energy density that's associated with empty space. If you go to the middle of the Bode's void and take a cubic meter of space, there's energy density in that space, not traditional energy. You can take all of the photons out of it, no mass of any kind. There's energy density in that space. Now imagine that you've got a room, and one wall of your room is a piston. It's a cylinder, and it's airtight. Now, if you pull that piston out and double the size of the room, and no air can get in around the piston, what happens to the air pressure in the room? It drops in half. Suddenly you're at 17,000 feet, gasping. In space, when you're talking about energy density, though, if you pull that piston out and double the volume of space, the energy density doesn't change. So there's extra energy that has to be in that space to keep the energy density the same. And where did that come from? Well, if you had a piston, it would be the energy from the hand pulling the piston, transferring into the space. But in space, there's no piston. So what the universe does is when you have energy density in a larger space, there is inevitably present in that space something called negative pressure that counts the positive energy density that has to be there to fill this extra space. And this negative pressure operates in 3 dimensions. It's 3 times more powerful than the gravitational effect of the energy density. Okay? And because it has negative pressure, it keeps the ledger of energy equal. You have negative pressure counteracting the energy density. Now that negative pressure, because it's more powerful than the energy density, causes something called gravitational repulsion, and it causes an expansion to occur.
To expand the universe, it takes energy.
And it's like free lunch in a way.
Every minute that goes by, the amount of energy has to be increasing.
Yes, but so does the negative pressure. And that negative pressure keeps violation of conservation of energy from occurring. And it also propels the expansion. It's almost like a magic trick. That's exactly the discovery that many of you are familiar with Alan Guth coming up with inflation theory in 1979. a theory that's been under attack for 42 years and still reigns supreme in the world of cosmology. And what he realized one night, he realized that Albert Einstein had created these formulas that determine how you determine gravitational attraction. He said, if you have matter, okay, matter causes gravitational attraction to occur. You convert the matter to traditional energy. If I convert this clock to energy, that too creates gravitational attraction that's equal to the mass that creates energy. Now let's take a region of space where you have no matter and no traditional energy at all. There are two other things that Alexander Friedman realized from Einstein's equations that also create gravitational attraction. One is energy density, which is that basic fabric of space, if you will, the Higgs field, the dark energy, and also pressure can create gravitational attraction. Positive pressure pushing up creates some gravitational attraction. These things produce gravitational attraction at a vastly lesser rate than traditional matter and traditional energy. So much so that you divide by the speed of light squared, okay? It's tiny, tiny amounts of gravitational attraction that are created by these. But then Guth realized, well, wait a minute, if I've got empty space, if I've got this little universe that suddenly for some reason has excess energy density, it's also going to have negative pressure to counteract the extra energy density. So what he realized is that somehow through a quantum fluctuation, a little region of vacuum ended up with too much energy density. And because of that, it had to have negative pressure to counteract it, to prevent a violation of the conservation of energy. And because pressure 3 times greater, okay, than the energy density, because it operates in 3 dimensions, the negative pressure ended up causing gravitational repulsion. Okay, positive pressure was not there. It was negative pressure. It was a suction. And so because of that negative pressure in the system, it created gravitational repulsion that caused the universe to inflate. And it's the same principle that now helps expand the universe today. As the space gets larger, we have extra space, we have extra energy density, extra negative pressure, and the expansion continues.
Is this energy density measurable?
Yeah.
How do we do that?
Well, I don't know exactly technically how it's done, but it certainly can be.
It's the only way we know it's there, right?
Yeah,
That it can be measured?
Yeah.
Mm-hmm.
But we don't know what it is, right?
Well, dark energy, we don't. The Higgs
Right.
field, we now do.
Okay.
Dark energy is the big mystery.
So with, I know a little bit about how they measure dark energy. So with dark energy, they take standard candles, so type 1A supernova in distant galaxies, and try to measure. So we have a constant light source, and so as you go further and further out, you can measure the dark energy density as you go further and further back in time.
Yeah, it's very clear. Thank you.
There's very little about this topic that we would call clear, I think.
Yes, right.
I got a personal question I'd like to ask you. What was or is your profession, may I ask?
I'm an attorney. But I've been doing astronomy a lot longer than I've been doing law. Okay, so.
So you specialize in obfuscation, or?
No, I try not to.
It's,
Try to be clear.
I got here quite late, but I'll have to say that you do as good a job explaining some of these things as anybody I've ever listened to.
Well, thank you.
Yeah, right.
I think we could do this for 8 hours, keep asking you questions, because we don't seem to have tapped it yet.
Actually, this is the most questions I've gotten. It's a risky program in the sense that I realize how long I've worked to understand these things. Okay.
Right.
And or
Right.
to try to. And I've had the advantages I alluded to earlier of growing up with people who became professional astrophysicists, including Richard Gott at Princeton and others, and they're great friends. And I talk with him on the phone every night and will again in about 2 hours. And so I've had the ability to keep up with developments through them and to ask questions, and that helps a lot. Some of this is not easily explained. All I wanted to do really tonight is just point out that because of the speed of light and because of the expanding universe and that pool analogy, that there are limits on how far we can see. And that was my goal. And this got carried into a lot more cosmology, which I think is a tribute to all of you, because obviously you've done a lot of reading on it. I can tell just by the questions, which have been fantastic.
Well, we would love it if we could do it again sometime.
Well, I have certainly easier listening programs than this one. Okay, so I do a variety of other programs. This is probably the diciest one I've attempted, but
He gave me a whole list and I picked the tough one. I was like, I want to learn more about that.
it only got tough at the end.
Chuck, is there any, have you recorded any of your other presentations that we could tap into? Because obviously we can't have you here. I mean, I think we'd love to have you here like once every month forever, but
Listen, I love doing it. I love doing them. So I'll come back as often as you want. And I promise you there are other programs that are much perhaps less demanding. But
well, I say we make you a member, and we can have a lot more of these presentations. How's that?
Yeah, I think some have been recorded on Zoom programs, but I didn't record them myself, so I'd have to figure out where they are.
Chuck,
Yeah,
do you do any public programs?
Oh, right, yeah.
You do, okay,
Well, I mean, I haven't during COVID.
right,
It's all been Zoom since
Mhm.
basically last March, but
right.
I had done probably 400 in-person programs before then. Yeah.
Great.
I've
Okay.
done some Zooms before then, but not as many as since COVID
Mhm.
started.
It'd be a real pity, if you didn't record or, some of these presentations and save them to share with others. I would certainly love to see tons of them.
Well, I'll see if I can dig a few up, or maybe I think if I recorded them, I'd probably want to record them myself, studio style, and then, rather than rely on somebody recording a Zoom program.
Yeah, well,
Yeah.
I want to thank you very, very much for
Well,
a
I
fascinating presentation.
really appreciate the invitation, and I hope you'll have me back. I'm sorry I can't be there in person. I hope that'll happen soon.
Yeah.
Yep, yeah, absolutely.
Not that big a drive.
Yeah. Chuck, we started by fits and starts putting some of the programs that we get on Zoom, we record them and kind of chop off some of the yik yak and put them on YouTube, but we only got a couple up there. But we'll probably put you up there
That's fine.
unless you got some copyright or something. But
No,
well, I
No.
could send you a link or something, but just go to YouTube and search for Fort Wayne Astronomical and you'll see probably a whole 2 of them or something. I think we got, we probably got 5 or 6 in the bag, but it just takes time to, put them together, so there you go.
that's fine. I'm happy to do that.
Okay.
Once again, Chuck, we're delighted that you are here with us tonight. It's been fascinating.
Well, I really appreciate that. It's been, honestly, I've enjoyed this presentation of this program to you more than any club I've done so far. So it's been, the questions have been fantastic.
We hope to keep us on the top of your list.
You are.
Amen.
Indiana's like a home state to me. My club's in Indiana, my observing site's in Indiana, and I live just a couple miles from Indiana. So you know, it's, I just wish I could get up there more often.
Do you snow ski at Patoka Lake?
I snow ski a lot, but not at Patoka.
Okay.
There's no skiing there.
There used to be.
There used to be?
Yeah, oh yeah, there's a lift somewhere out there, yeah.
Really?
Yeah.
Oh, you know, I think I've seen that.
Yeah.
It's very
Yeah.
small. Yeah, I think I do recall seeing an old
Yeah.
chairlift out there one time wandering
Oh,
around.
well, it's expanded now and the time has gone by.
No, it's under a gravitational field.
Yeah. Yeah, I drive 72 miles to my dark sky side, and I do it every chance I get. So
Wow,
it's a
long way.
nice secluded area.
Mm.
Thank you very much.
Okay, thank
Yeah,
you.
Thank you, thank you.
Good being with you all tonight.
Thanks.
Good night. Okay,
Thank
Good
you,
night,
Chuck.
Chuck.
bye-bye.
Bye.
Thank you.